Okay, so today's topic is on gravity and projectiles, and I've got a few different demonstrations I'm going to do. So for anybody who's watching this as a YouTube video, obviously that won't make sense, but for you guys watching here, I want to begin with a history lesson. I'm going to drop two objects here. Actually, I'll rip a sheet of paper off. You guys ever heard of Galileo Galilei? Galileo? Heard his name before? He liked to challenge. You guys, you with me? He liked to challenge the preconceived notions of physicists, and before Galileo came around, there was a theory. It was actually based on Aristotle. Aristotle believed that heavier things fell faster, and they actually had evidence for it. I am going to do an experiment here that's going to prove to you that heavier things fall faster. Ready? Here's my book. It's pretty heavy. I mean, in the grand scheme of things, compared to this sheet of paper. I'm going to drop them both. That one fell faster. And for years, physicists believed that heavier things fell faster. What were they not accounting for? What was that? Drag force, yeah. Because what ends up happening is, like when you make a paper airplane out of this thing, right? You throw the paper airplane will actually ride on top of the air because there's air underneath these objects, right? And this lighter one right here kind of was floating down. Now, it made sense to some degree that heavier things fell faster than lighter things, but Galileo wasn't convinced. And so he tried to find a way to remove drag. So the legend goes, and I don't know if this is true, but the legend goes that he took two cannonballs. Probably a convenient thing at the time because this was like the 1600s, I think. So he takes two cannonballs, one that's like big and one that's small, and he carries them to the top of the Leaning Tower of Pisa. You ever heard this story before? He takes the two cannonballs, puts them over the side of the Leaning Tower of Pisa, drops them at the same time, and more like this scenario here. Here are two objects that must not have the same weight, and when he dropped them, when aerodynamic drag was reduced, they landed at the same time, right? But if this one right here has some drag and this one right here doesn't, it appeared the heavier object landed faster, right? So, long story short, Galileo had a new theory then. He suggested that gravity affected all things regardless of mass. Mass really wasn't the important thing. The other thing he suggested is that gravity must be affecting things in a manner which is accelerated motion, non-uniform motion. That was his suggestion. Things got faster and faster and faster. They weren't traveling the same speed as they went along. One was accelerating. We can even see that as I drop these two objects. This one right here accelerated faster, 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 faster. This one was kind of going the same velocity the whole way down. I want to do a little demo here. I made a little a manipulative to hopefully help show this. It worked pretty good in my Mod 10 class, so hopefully it'll work for you guys too. What I've done is I've put on this string right here, there's a whole bunch of screws or nails on here, and I've put them the same distance apart. So from here to here is the same from here to here to here to there. So they're all the same distance apart. Now, before Galileo, the thought was, well, maybe gravity pulls things all at the same speed. Which means that if I were to let this go, here's what you would hear. You'd hear it go clink, 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 clink. And all of those clinks would be the same distance. Does that make sense what I'm saying there? That's what they thought. Everything was going the same speed. Galileo suggests, no, I think it's accelerating. I think what's going to happen is rather than it going all at the same time, if I were to visualize that even, the suggestion would be rather than them going 1, 2, 3, 4, 5, 6, all evenly spaced, the suggestion is maybe the first one goes like this, the next one happens a little bit quicker, the next one happens even quicker than that, the next one happens quicker than that. And he suggested, I think this is what's supposed to happen. This guy right here would be uniform motion, where everything's nice and consistent. He suggested acceleration due to gravity is actually, well, accelerating. So I want you to listen to this. Rather than it all going all at the same speed, clink, 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 and it goes fast, so you kind of gotta listen real careful. But listen to how this sounds. You probably heard dun dun da da. Does that make sense? You probably heard two clinks, and then after that, the remaining 6 clinks all happen like nothing else. Listen again. Listen for 2 fairly distinctive clinks, and then all the rest more or less happening all at once. Of course, it gets tied up every time. One more time. Yeah. Of course that doesn't work. is not the most foolproof one I have, but we'll make it work. That's pretty good. Could you hear that? It didn't go dun 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 dun. It went dun 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 dun. Right? It sped up. I mean, any of you guys who are musically inclined probably understand playing on the beat, right? You play a metronome, it goes ch 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 ch, right? And this is accelerating. It's getting faster and faster. And so I can even illustrate that with this diagram here that starts my notes. Imagine that you were to shoot an object, any object. Let me move out of the way so I'm not standing here. Like, say, a cannon off the top of a cliff. Well, what we recognize is that this is really the way that the motion happens to go. It would ideally go in a straight line, but gravity is going to start pulling this object down. Now, I want to really focus on the distance it travels. In the first unit of time, it only falls a little bit. But then in the second unit of time, it falls a little further. And in the third unit of time, it's fallen even further. And in the fourth unit of time, it's fallen further than that. Can you kind of see how none of these are uniform? If it was uniform, it would have literally gone in a straight line like this, and it would have gone this far, and then it would have gone the same distance, and the same distance, and the same distance. But that's not what happened. Let me undo all that, because that got really messy all of a sudden. The distance that it fell was, say, like 1 meter. In the next second, then it fell 2 meters. Then maybe it fell 4 meters. Maybe it fell 8 meters. There's a bit of a pattern to it, but it's not a linear pattern, which is a nice direct relationship of like constant speed. It's getting faster and faster. And so that's what we recognize gravity to be now. I've got a few slides that talk about this. So here's my first slide that's got some more information on it. The word we're going to use is called a projectile. That's the generic word we use whenever we're describing something that is basically being thrown in the air, tossed up and down. Like any sports object would be a projectile. And the important thing is we only consider the only force to be gravity. We are going to ignore air resistance. Even though we recognize that air resistance is what was causing heavier objects to appear to fall faster than lighter objects, for the most part in this course, we're not going to calculate any sort of friction, drag type numbers. We can, it's possible, but we're not going to. We're going to assume there's no air resistance. And the three main types of scenarios we can have look like this. We either drop an object, and can you see how like this right here kind of helps illustrate the fact that this is not uniform motion? This one to this one to this one to this one, they all have slightly different distances between them. That's not uniform. Here is someone throwing an object straight up and down. All the way up, all the way back down again. And then here's someone lobbing it forward. And they really all have the same sort of pattern to them. And it really helps if you've done math 20-1 or 20-2 already. If not, sorry, I'm going to give you a quick tutorial. You're going to learn this at some point. This shape right here is known as a parabola. Some of you familiar with the term parabola, hopefully? And so if you haven't done this in math at some point yet, you should in math 20-1 or 20-2. This is a very, very famous shape. It's a parabolic shape, and it kind of has some very similar properties, two of which I want to point out. The first is that parabolas are always symmetrical. You can always cut them directly in half. They have what is known as an axis of symmetry. Any of you guys talk about that in a math class at some point? Good, I'm seeing some nods. And there's one more property of this sort of shape that you're going to learn, or you should have learned. The very, very, very peak of this parabola right here, the very, very top, has a name. We call it a vertex. Vertex. And the vertex is special because it's the point where the object is up in the air and it kind of like hovers for a second. Right? If you can imagine, I don't know, a volleyball athlete jumping or a basketball player taking a shot, and you're jumping up in the air, and like as you're at the peak of your jump, you kind of like hover for just a second before you come back down. That's this point right here at the very, very, very peak of your jump. Here's a slide that just talks about the story I already told you. Historically, Aristotle thought that mass was important. If you were heavier, you fell faster. But they also were wrong. They thought they fell with constant velocity. So there were two errors before Galileo came around. Error one, they thought that mass made things fall faster. That's not true. It doesn't really matter how heavy it is. And the other problem is they thought that things were always falling with a constant velocity. So if you were a heavier object, you would fall faster. We're wrong about both of those. These things accelerate. When I dropped the little keys into the screws into the container there, it didn't go dun, 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 dun. It went dun, 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 right, as it got faster and faster as it went. And we also know now that mass is really independent. It does not matter how heavy the object is. In a vacuum, or in a location where air resistance really doesn't matter, it should always be accelerating at a constant rate. Now, hopefully you've already been taught this a little bit in Science 10. Hopefully this wasn't like brand new. Maybe I supplemented it a bit. But at the very least, I hope you guys have seen this number before here. 9.81 meters per second squared. Okay. It's a value you should have used at some point in grade 10 physics. And we often use the letter G to denote it. It stands for gravity. It's the acceleration due to gravity. Now, technically, that's actually not true. The actual value we believe to be this number right here, 9.80665 meters per second. That is a very precise number. Let's talk accuracy and precision again. That is a very precise number because it has so many more digits. One of the problems with it, though, is that this number is dependent on your location on Earth. Weird thing, but gravity actually, I'm gonna close the door there. Gravity actually applies stronger closer to Earth's surface and not as strong further away from Earth's surface. We know this already. Let's say you're going up into outer space. How much gravity is there in outer space? Well, like none. Okay? So the further you go up in altitude, the less gravity there is. And so what I mean by this is that in certain locations on Earth, depending on your altitude, I can't spell altitude. Altitude. Depending on your altitude, how high above you are above the Earth's surface, depends on where gravity is at. So the average value on Earth is 9.80665. But that has too much precision for us to know for sure all the time. So normally we round it to 9.81, and we use this number because we're fairly certain that regardless of where you are on Earth, whether or not you're in Vancouver, which is at sea level, whether you're in Lethbridge, which is 900 meters above sea level, or if you were on top of the Rocky Mountains, which is a few thousand meters above sea level, it's probably 9.81 regardless of where you're at. Does that make sense? It's a good way to talk about accuracy and precision. This number here is very precise, but I don't know that I have confidence in every single one of those digits, because this number does change depending on where you're at. So the only thing I can know with confidence is let's be confident about 3 digits. That I know I'm sure of. All right, anyways, let's move on here. Let's try an example. A large steel ball gets dropped from a height of 7 meters above the floor. Tell me with what speed, what velocity the object will strike the floor. Now, as you look at this question, it may seem, Chris, you only give me one number. How can I do an example with one number? But that's not true. Okay, we have a height. That's really a distance. It's going to travel 7 meters. Stop that. Distance 7.00. But we actually know a few more things. It just didn't say it in the question. We know gravity. We know the acceleration due to gravity is 9.81 meters per second squared. There's also one more thing we know. It's really subtle. You know what the third thing we know is that it just didn't say? You're right, initial velocity, yeah. It said it was dropped. That implies that the initial velocity was 0. You know what? We do have enough to solve the question. So far, in our kinematics equations, you need to know 3 out of the 5 variables. What are the five main variables? Distance acceleration, velocity initial, velocity final, and time. As long as you've got 3 of the 5, you're good to go. You just need to pick the right formula. So we do have 3 variables. If it asks for what velocity the object strikes the floor, we're looking for velocity final, which is the right formula now. So hopefully, as you've been working through the first assignment, and as you've been doing the lab, you're getting more familiar with these formulas. This is probably the formula you want. Vf squared equals Vi squared plus 2AD. Because it involves velocity final, velocity initial, acceleration, and distance. So, next step, we want to isolate for the variable we want, which was velocity final. So if I just square root both sides, solves that problem. So here's my formula. Velocity final will be equal to the square root of velocity initial. Well, that was 0. Okay, 0 squared. 2, acceleration due to gravity was 9.81. And the distance, what was it, 7 meters? 7 meters. What? It's going to be calculated. Not bad. So let me grab my calculator and try this one here. 2 times 9.81 times 7. And when I square root the whole thing, I get this number here. I'm going to write out the whole number because I want to use it to maybe make a point. I really want to make sure you guys understand accuracy and precision. I got 11.71921499. That's what my calculator spits out. That is now an exceptionally precise number, right? I mean, it just has way too many digits. Do I know with confidence that this number right here is for sure a 2? No. Right? And that's the problem, is that accuracy and precision go hand in hand. I have too much precision for what I can guarantee. I can't guarantee I keep all these numbers. So the rules we have for sig digs are pick your lowest number of sig digs, 3. So round this down to 3 sig digs. The only thing I can guarantee is that I know that it's up to 11.7. I can't guarantee anything more than that. You guys know how you get like a warranty on something for a year or something like that? I'm going to give you a warranty up to 11.7. That's all I'm going to guarantee. Could the next number have been, well, whatever was, what was underneath that, a 1, I think? Could it have been a 1? Could have. Could have been a 2. I wasn't willing to bet on it. Does that make sense? So there's my answer, 11.7 meters per second. I can only be as accurate as that. Any questions? Okay, let's try another one. This is one of the downsides to doing like the group lesson. I'm sorry if I'm going too fast for you or too slow. Next week, Monday though, well, 2 weeks Monday when you guys come back, when we do the lesson on vectors, bring headphones. That's the lesson I want you guys to try by yourselves. That way, if I'm going too slow or too fast, you can speed up. Let's try another one. Say there's an amusement park ride, and at the crest of the rise, you begin a vertical free fall. So just so you understand what I'm saying, this is one of those things where like you're about to go up to the top, and this is like the drop of death. You know, I mean, they'll probably let it even out at the end here, otherwise you die. But that's what we're going for, is the drop of doom right here, where your little card up here, here's you. You're about to go whoop, right over the edge. Again, I only gave you one number, 1.5 seconds. Not true though, there's hidden information here. Sure, I know the time was 1.5 seconds, but I know acceleration. Gravity is 9.81. And one more thing. It says that at the crest of the rise, you began a vertical free fall. It was kind of implying that like your velocity initial was 0 again, where you were just barely about to nudge over the edge. Because here's the thing. If you went over this edge with any speed whatsoever, you wouldn't fall like this. You would go out like that, and that would cause some problems. Does that make sense? So it didn't say as much, but it kind of implied that you're going to have to literally have no velocity, and someone just goes, and you just barely fall over the edge. Does that make sense? Because if you had any velocity going this direction right here, you wouldn't fall straight down and get caught by the S pattern here. You'd like, yeah, anyways, hopefully you get that idea. Okay, we have 3 variables. Anytime we have 3 variables, we should be able to solve. I asked you for the distance traveled, so let's use this formula here, D. The formula is D equals VIT plus 1/2 AT squared. The formulas we're using today aren't any different. They're the same 6 formulas we've always used. Actually, this one's pretty easy. All the numbers are already ready to go here. Velocity initial was 0. Time was 1.5. Acceleration was 9.81. Time was 1.5 squared. Just plug her in your calculator. Again, I'm going to do this just for effect. I got 11.03625. I cannot guarantee all those numbers. There is no warranty on this number right here, for sure being a 6. I cannot guarantee that number. Because you know how we use the value 9.81? What if it was actually 9.80655, whatever the number was there? Wouldn't that change this number a little bit? And I can't guarantee the 6. So based on my sig digs, I believe I get 2 sig digs. Because the time value had 2 sig digs. So if I only get 2 sig digs, we gotta round this thing generously to the nearest ones. Remember how I talked about accuracy and precision before? When I ask you what precision you chose, this is a number rounded to the nearest ones. Make sense? All right, one more thing then. We were asked to solve for the distance. We've done that. We were also asked to solve for the final velocity. So let's pick a different formula. So I'm going to find a formula that involves time, acceleration, velocity initial, and velocity final. So this is a good formula to use here. Acceleration equals your change in velocity over your change in time. And the reason why I want to point this formula out is kids forget to use this one because it doesn't look like it has 4 variables. It looks like 3. I mean, you look at it, you go, Chris, I see A, B, and T. There's only 3 things there. Count, Chris. Come on, count. But it's kind of sneaky. This formula, the delta V, really implies final velocity minus initial velocity. Anytime you have a delta, it implies you're subtracting the difference between 2 numbers. So we really do have a formula with 4 variables. It can actually be written as velocity final minus velocity initial over your change in time. There we go. Now I do have 4 variables. So we're looking for velocity final. Use your awesome algebra skills to rearrange for velocity final. You would have to times the time value up, and then you're going to have to add VI to both sides. So it's going to look like this. Your acceleration will times by your time value. I'll put an X there. Acceleration will times by time. You'll add it to VI. Now you get VI. Okay, acceleration was 9.81. Time was 1.5. My velocity initial, though, which is good, though, right? Because here's the thing. Let's say that we gave you a push over the edge. Well, then we'd be adding more speed. And we might not want any extra speed. We might be going fast enough. Now, granted, this is only after 1.5 seconds. It's not that long. But I don't think we need any extra speed. So that one was 0. So 9.81 times by 1.5. Again, I'm not going to do this anymore, though. But again, I get a value in my calculator of 14, etc. I often write it as like 14 with like some decimal places. And I just kind of write dots to kind of imply there was a bigger number there. With 2 sig digs, it rounds to 14. Oh, no, it doesn't. It rounds to 15. Come on, Chris, get on top. It rounds to 15. There was a 7 here. So it rounds to 15. That makes sense. Now, one thing I could point out is that I chose to use this formula here. But I could have used a different formula. I could have used the formula VF squared equals VI squared plus 2AD. Because I do know the velocity initial. I did know the acceleration. And didn't I solve for the distance at some point? Okay. Now here's the thing I want to point out, though. Let's say you use this formula. You cannot plug in the number 11 meters. I think we solved for 11 meters at some point here. 11 meters right there. If you are going to use a number that you've calculated again, the way you do it properly is you have to use the 11 points and use all those numbers afterwards. The reason why is if you keep rounding numbers over and over and over again, you start to lose some of your accuracy. So even though we don't believe we should be keeping all of these numbers when we get a final answer, if you're going to use that number a second time, use the whole number if you can. There's actually a way of saving that in your calculator. Let's see whether I've got a calculator on the screen here I can show you. Here is an app for a generic graphing calculator. If you ever need to save a value, for example, you need to do like 8 divided by 3, and it gives you a number, and you want to use like that whole number. You don't want to round it at all. Here's how you can save it. Right here above the on button is a button called STO. There's a little arrow. It's called storing a number. Press that button. And what it's going to do is it's going to take your answer and store it as any letter that you want. And your calculator has letters. If you press alpha, and then almost any key on here, like that one right there, that will now make it be a letter. So I can now store this as X. Or I could store this as the letter A. So if I do that, now it's been stored as A. If I now take 5 and times by the letter A, it will basically take this number right here and times by 5. So it's like kind of a nifty trick for saving numbers when you use them in subsequent calculations, which we will have to do at some point. So if I'm asking you for a final answer, yeah, you need to round. But like if you're going to use that number again later, don't round. You're not done yet. That makes sense? All right, I'm going to go back to full screen again. The next couple slides I'm going to talk about, one of the problems is that we're assuming something. We're assuming low aerodynamic problems. We're assuming there's no drag, basically. Remember that whole initial flaw where I dropped a sheet of paper in my book and the sheet of paper fell afterwards? We now know that it's due to drag, air resistance. And one of the ways we can kind of almost visualize this is that gravity is pulling something down. But there are particles of air. We can't see them, but there are particles of air. And if you have an object that maybe isn't a cannonball, but that maybe is like a flat sheet of paper, all those particles of air are going to kind of push back up on your sheet of paper. This is a good thing. If it wasn't for like lift and drag, we'd have no airplanes. Like, how do airplanes stay in the air? Yeah, I mean, they literally float on top of air. Right? It's not that they're traveling so fast that gravity doesn't make them fall. It's that they're so spread out with those wings that there's enough surface area to keep all of these air particles underneath them, and they stay afloat a little bit. So if you can achieve a scenario where the amount of gravity pulling down equals the amount of drag force, this would be like an airplane. It can stay in the air. However, let's say you were already traveling, you were already free falling. There's a term called terminal velocity. What it basically implies is that anything falling through the air reaches a speed at which it can't speed up anymore. Like, it cannot go any faster because there's going to be at least some amount of air particles underneath causing drag. I don't know if any of you have gone skydiving, but if you can imagine a skydiver like I have in this next picture right here, a way a skydiver slows himself down or herself down is they put their arms out to the side. What does that do? Well, it causes there to be more surface area. More surface area creates more drag, and it slows you back down. Let's say that you want to go as fast as you possibly can. You like go all Superman with your arms like in a point because you're trying to like slice through the air. And I found this slide right here that kind of illustrates different sorts of objects and what their drag coefficient is. Let me use one that you're probably familiar with. A long shape like this. This is a horrible drag coefficient. So bad that in southern Alberta, when we have trucks, like long-haul trucks, that are in windy conditions, when the wind keeps hitting the side of the container over and over and over again, it can cause those trucks to tip over, right? Because basically that's the same thing. The air is providing a lot of drag on these things. One of the most aerodynamic shapes is actually this one right here. We try to use this when we're trying to design things like bullets, or cars, where we want to try to make it very streamlined, right? Where the air is going to kind of go over the front and then it kind of like slide over the back and become aerodynamic. Does that make sense? Right. An old 1988 Buick, if you've ever seen one of those kind of cars, they're big boats, right? They're not very aerodynamic. But if you had like a Ferrari that you'd be driving in like the Formula One circuit, that thing is probably low to the ground, really sleek and streamlined, right? It's trying to cut through the air a little bit faster. Now, there is math for this. It is possible for us to do equations to calculate how much drag. I found this on NASA's website. We're not doing this. Don't write it down. We're not ever going to do this. But I want to let you know it is possible to do these calculations. We're just going to skip them every time. If you want to calculate out drag, you would need to know the velocity you're traveling. Apparently, you need to know the density of the gas you're traveling through, which is like your atmosphere. You need to know how much area you'd have, like frontal area. So like that would be back to these shapes right here. If you had like an area that was like kind of streamlined versus like a big box, that makes a difference. And finally, you need to know your drag coefficients. If there is a way to calculate drag, we're just not going to ever do it. Make sense? Try another example. And I'm going to actually do a little demo with this example. And I made a typo here. So I need you guys, if you're writing this down here, change that to the word up. And maybe write it down while I get some of my demo ready to go here. So I'm going to pause for a second, get my cap gun, my dart guns ready. We got dart guns today. With all the cool toys in physics, right? Hot Wheels, dart guns, lasers. Okay. So the scenario I've got right here is a person is going to throw a ball up from the top of the cliff. And if I were to draw this real quick, maybe I'll do that before I do my dart guns here. Imagine there's a cliff here. There is a person. They're going to throw a ball up off the top of the cliff like this. Again, for those of you who've done your 20-1 or 20-2 math class, you should recognize this shape. This is the perfect parabola shape, right? It's going to go up in the air, and it's going to fall back down again. And I want to represent this rather than just doing a picture. I've got my dart gun here, and I'm going to shoot it up in the air, and of course it hits the roof because it's too strong. So I figured out a way to solve that problem. The way this dart gun works, you have to listen carefully. As I put the dart in, you can hear it click at different levels. Listen here. There's 1, 2. So if I don't click it all the way in, it won't shoot it as far. So now if I do this, we get a nice parabolic kind of shape. So what I want to do before I solve the rest of this question, though, is I want to illustrate an interesting phenomenon. Okay, I'm going to click this in twice. 1, 2. Here's what I'm going to do. I'm going to shoot the dart straight up in the air, more or less. And the dart's going to go up in the air and fall back down. And what I'm going to do is as soon as the dart gets back down to level with me here, I'm going to drop the second dart. Does that make sense? And we just want to see which one hits the ground first, whether they'll hit at the same time or whether one will be quicker. Does that make sense what I'm suggesting? So shoot the dart up in the air. It'll come back to here. As soon as the dart gets to here, I'm going to let go of the other dart. We're going to see which one hits the ground first. Which one hit first? The one I shot. But that doesn't make sense. Weren't they both right here at the same time? Shouldn't they have landed at the same time? Well, but this one was already in motion, and that's the thing we want to discuss here. So this guy right here, as I shot it up in the air, one more time, I'll do it again. Okay, I probably let go a little too soon, I think. Try one more time. 1, 2. See how this one hit faster? The reason why is that the one that came out of the gun, it was already in motion, right? It was already moving, right? It wasn't starting from rest right here. It was starting from rest up here. Right? Remember how I talked about like a basketball player hanging in the air a little bit as they're at the peak of their jump there? Well, this dart that was up in the air, as it was up right there, it was kind of starting from there. This guy got to start here at 0. By the time it got back to level, it was already traveling faster. I want to try one more example, but with 2 dart guns. Watch this. I'm going to make both of them the same here. I'm going to do the same thing. I'm going to shoot one of them up in the air, and the other one, as soon as it gets to the same location, I'm going to shoot it down. Okay? So rather than letting it go, I'm going to give this one some speed as well. So it's going to go like this. They almost landed at the same time. Watch that again. So rather than dropping this one and shooting this one, I'm going to shoot this one up. And as soon as this one gets back down to like level here, I'm going to take this gun, turn it upside down, and shoot it. See how they're going to go at the same? They're going to land at the same time now. I was a little behind. One more time. 1, 2. 1, 2. Okay, so shoot this one up. See how they landed at the same time? Because this one went up and then came back down, but rather than dropping the other one, I shot it. And they're both going the same speed. I want to show you how that works on this picture right here, because there's more of a theory principle in play. So using that demonstration as our guide, it says that we threw the ball 12 meters per second up. What that means is at this point right here, the ball was going 12 meters per second. However, I can tell you this. At this point right here, it was traveling down at 12 meters per second. However high it was shot up in the air at, when it gets back down to that same point, it's going the same speed. And the reason we know that is through some math principles of how parabolas are symmetrical. I mentioned this earlier. If any of you guys have taken your math course before, these parabolas you have, they get cut exactly in half. They are symmetrical. And so whatever the speed is right here going up, it's the same speed here going down. What's the speed right at the vertex? 0. If it went straight up and then back down again, at the very, very, very peak, it should have stopped for a second. Okay? Now, I know I'm kind of shooting it outwards, but imagine I shot it just straight up and straight back down. What should happen is it should go 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. It should be exactly symmetrical. That's a really important principle I need you guys to know, is that the speed that it shoots up in the air is the same speed it lands with. There's a scenario in life where this is actually kind of important. Remember, I don't know, like an old Wild West kind of saloon kind of things? The guy with the cowboy with the guns shoots the bullet straight up in the air? It's actually kind of dangerous to do, because if it goes straight up into the air at 200 feet per second, it's coming back at 200 feet per second. Except here's why it's actually not quite that bad. There is air resistance. Okay? And so because there is air resistance, it slows it on the way up and it slows it on the way down. You still shouldn't shoot a gun straight into the air, because, I mean, what goes up must come down. But in theory, if there was no air resistance, if you shoot it up at 200, it's going to land at 200. So, let's do our question now. I wanted to use that to illustrate some theory concepts. Let's finish off this question. Question 1. It asks us to figure out how fast this object is going to be traveling after 3.45 seconds. So let's write out what we know. I know my velocity initial was 12 meters per second. I know that my acceleration is 9.81 meters per second squared. And I know that my time value is 3.45 seconds. Those are the things that I know. Except one of them's wrong. Okay. Good. And that's what I want to illustrate in this example here, is that for the first time here, we really need to make sure that we designate a positive and negative direction. Since velocity was going up, but acceleration was going down, we have to designate properly with positives and negatives. In all the previous examples, it really didn't matter, because we were always just traveling down. But if we go up, then down, now it makes a difference. So yeah, we have to use a negative for our acceleration. So it asks for how fast is it traveling, so that's velocity final. So there's my question marks. So we need a formula. We already used this formula earlier today. It was acceleration is equal to velocity final minus velocity initial over your change in time. And when you rearrange this for time, you get acceleration times your change in time. What are we solving for again? Velocity final? I think I said that wrong. We want velocity final. We need to add velocity initial. There we go. And now we'll get velocity final. I think I said it wrong, but I think I'm doing the math. Does that make sense? Plug in your numbers, but be careful about the negatives. The acceleration is now negative 9.81. Your time value is 3.45, and your velocity initial was positive 12. Negative 9.81 times 3.45, add 12. With sig digs being 3, it looks like. Oh, 3? 2 sig digs. With 2 sig digs, I get negative 22 meters per second when I round it. First question, negative? Should you get a negative velocity? Oh, yeah. Because when you shot the ball up into the air, it's a positive velocity, but I bet you after 3 seconds, it's on its way back down, right? Unless you shot it really high up into the air, it's probably on the downside, right? So then a negative velocity makes sense because it's now on its way back down. Remember how I told you that on the way up it had a positive 12 velocity, and right here would have a negative 12 velocity. Negative 22 must be somewhere down over there. Did everybody else get negative 22? Got it. So that was question 1. Then it asked another question. It said, when is the ball at its maximum height? What do we call that maximum height again? What's the name of that mathematically up here? Vertex, yeah. And the property of the vertex that matters is that as the object is up in the air, for one brief second, it stops before it kind of comes back down, right? You're going all the way up and then fall, right? And for whatever reason, like, basketball players are a great example of this. Michael Jordan just had this ability to, like, do his fade back jumper and just hang for forever, right? It's what gave him the ability to separate. Anyways, basketball overlap. What we know then, if we're going to change this question up a little bit here, is that of these values, some of them are still the same, some are different now though. So I'm going to erase and start over now. My velocity initial is still 12. That hasn't changed. My acceleration is still negative 9.81 meters per second squared. But I know that my final velocity is going to be 0. At some point, right up here, it's going to stop for a quick second. So when it says, when is the ball at its maximum height, I'm going to solve for time. So I'm kind of using the same formula I've been using for the last few examples. I just have to rearrange it now for the time value, not the velocity final. So acceleration is equal to velocity final minus velocity initial over change in time. To rearrange it, change these guys around. Change in time is equal to velocity final minus velocity initial over acceleration. I want to show you something here. This is really cool how this works out. Our velocity final was 0, right? Because for a brief second, it's going to stop and hover in the air before it falls back down, right? Velocity initial was 12. However, the formula calls for a negative sign. Okay, so the formula calls for a negative sign, but the velocity initial itself was 12. But the acceleration was negative 9.81. 0 minus 12 is going to give you minus 12, right? When you take a negative 12 and divide by a negative 9.81, what happens when you take two negatives and divide them by each other? You get a... But doesn't a positive make sense? We're solving for time. Can time really ever be negative? Yeah. Unless Stephen Hawking has read about black holes and stuff. We'll get there. No, we won't. That's beyond this course. Anyways, does that make sense though? Since time can't be negative, right? We just divide the two numbers here. What do we get? 12 divided by 9.81. I got 1.2 seconds. Which I think makes a lot of sense. Because if it takes 3.45 seconds for the ball to go all the way up in the air and then begin its descent, 1.2 seconds up here, that seems logical. And then one more question. It also said, what is this maximum height? So remember those core 5 variables, velocity initial, acceleration, time, velocity final. We just need to solve for distance. So pick a formula that works. Honestly, at this point, you can pick any formula you want. Right? As long as you use this time value of 1.22324159, as long as you use that whole time value, you can use any formula. So, I don't know. I'm going to pick this one here. Distance is equal to velocity initial times time plus 1/2 at squared. I'm going to pick that formula. The reason I like this formula is distance is already by itself, right? Like distance is already isolated. So let's plug in some numbers. My velocity initial was 12. My time, I have to use that exact value. So I'm going to actually store this 1.22324 number. I'm going to store it as letter A in my calculator, just so that I use the whole value. And so I'm not going to actually write 1.22 here. I'm just going to write the letter A, because that's what I'm going to use. A is really this number here. And I need 1/2 of acceleration, negative 9.81. And then time, that 1.22 number, I'll use A squared. So don't just use 1.2 seconds. You have to use the whole value. We'll round when we're done. 12 times A plus 1/2 of negative 9.81 times a squared. And with rounding, I got 7.3. 7.3 meters in the air seems reasonable. Right? Throw it up in the air, and it's on its way back down, right? So, it seems reasonable that this thing could have gone 7 meters up before it starts coming up its way back down. I mean, it was traveling 12 meters per second. That's pretty quick. Right? It's going to do 12 meters in 1 second. So the fact that it only did 7 meters, yeah, I think that's well done. Okay. Does that make sense? Sorry for anyone who I'm either going too slow or too fast for. It's the downside to doing a group lesson. Want to be pressing questions? Okay, last example, then we're done. On the last example here, it's actually a trick question. Has anyone ever heard of something called G-force, or how many G's something undergoes? Some of you are nodding. I think there was a movie about G-force that my daughters watched, like a Disney movie way back when. Anyways, G-force is something that like astronauts experience. Anyone ever seen one of those devices where they put the astronaut in the machine and it like pivots around in a circle, like a crazy amusement park ride, and like they want to see how fast they can get them to go before they puke? It's a training exercise, and one of the reasons why is that astronauts have to be able to withstand a lot of force, a lot of G-force. A G is actually a measure of acceleration. Okay? If you have 1 G, you are accelerating 9.81 meters per second squared. If you're undergoing 2 Gs, you're going 19.62 meters per second squared. Twice gravity. If you're undergoing 3 Gs, all you have to do is take 9.81 and times it by 3. A G is a measure of how much acceleration you're undergoing. So this is why this is a trick question. If I tell you that you're an astronaut undergoing 5 Gs, how fast are you going? You don't know. Because remember, speed is something that can change. And if you have acceleration, you're going faster and faster and faster and faster. Does that make sense? So if I ask you how fast you're traveling, I have no idea. If you were just starting, you were going 0. And then you got faster and faster and faster. Does that follow? So this is kind of a trick question. If I ever ask somebody about how many Gs you're undergoing, Gs is a measure of acceleration units, not how fast you're traveling. This was clearly non-uniform motion because it's accelerating. And since it's accelerating, we don't know how fast you're traveling. Trick question. Okay. I think we're about done for the day. I'm going to let you guys take off if I finish early. Let's do a quick recap of what we're going to accomplish over the next couple of days. And then you can go. We're done half our unit. There are 8 sections in kinematics. We've done 4 of them. So on Thursday, I want to do a check-in quiz. Let me talk about that a bit. You're already getting 100%, guys. Giving everybody 100. Because here's the thing. I don't want you to be worried about, oh, what if I fail this quiz? What if I do bad? That doesn't matter right now. And I know everyone kind of smiles a bit and goes, sweet, I got a free 100%. That's not my goal. Can you guys give me 1 second before you pack up here? I just want you to be listening here. My goal on Thursday is diagnostic. It's like the preseason, if you like a sports analogy. It's like a dress rehearsal, if you like a theater analogy. Okay? I don't care how you do tomorrow. In fact, I'd rather you, well, not tomorrow, on Thursday. I'd rather you really tank it. If you're going to make mistakes, let's find those mistakes and make improvements. And I want to give you a scenario, a fail-proof scenario where you don't have to worry about your marks. I don't want you to have to feel like you have to, worry about every little mark. Oh, what if I get this one wrong? Oh, I'm going to lose all my marks and I'm going to fail. I don't want you to have that attitude. So I'm going to give you a free 100%. What I want you to do is engage in the process of figuring out what you don't know how to do so we can make improvements. So that's Thursday. Thursday is going to be a practice quiz. It doesn't count because you've already got a free 100. Tomorrow, though, I want you to work on your assignment. You're going to get basically the whole hour to work. Okay. And by the end of the class, if you want to have unlimited redos, hand it in by the end of class. An honest attempt at all 8 questions. Is that fair? That's all I got. You guys can take off. If you got questions for me individually, come find me. Thanks, everybody.